Okay, so today I'm going to be making a video on indefinite integration with respect to multiple variables. So, in calculus 1 and 2, you focus on integrating with respect to x, kind of, or y, whether it be implicitly or explicitly. Um, but in higher calculus with multiple variables, when you have a function of multiple variables, whether it be polar coordinates, cylindrical coordinates, or just rectangular coordinates. Today, I'm just going to do x, y, and z. I'm going to make a video on converting from polar to rectangular to spherical. But today I'm going to show you how to do basic indefinite integration with respect to multiple variables. So if we use some function w equals f of x, y, and z. So basically what that means is that w can be written in terms of x, y, and z. So an example for w, for example, could be sine of x plus y cubed plus 4z. Now, this has an integral, or it has to have an integral because this represents a function. So, um, so the even though this doesn't represent a rectangular region, it represents some shape. So, for example, um, if we wanted to form a function f of x, y, where let's say we had some function z equals 4x plus 3y. This would form a region. This would form a plane in the third dimension, and we can calculate the volume under this surface if we give it definitive endpoints, like let's say 0 and 5. But for the purposes of today, I'm focusing purely on indefinite integration, so none of this. So basically forming a function that represents the volume under this surface from one point to another. So, and you might ask, okay, well, if I were to put 0 and 5 here, what does this really mean if there's one integral sign for two variables? Well, it means that this represents one variable in one dimension. It represents a line, a distance that you're integrating along. So for two variables or three variables, we're going to need multiple integrals. So if we wanted to take the integral of z equals 4x plus 3y, what we would need to do is we would need to take the double integral. So for this one, we'd have to take a double integral and this a triple integral. The double integral usually represents the area of like a region. And then the triple integral can represent the area of a volume. So how you can kind of think of it is like the reason the area of a double integral uh, the reason the double integral represents area is because you're essentially taking the integral over some line, then taking the area under that line, and you're compressing those two to form a shape. And so for this one, you might find if you shift the shape, it becomes a rectangular shape. So let's put our function in here. So we have 4x plus 3y. We're trying to take the integral of this. Um, and I'm not integrating from any area right now because once again, doing indefinite integration. Um, but our, we do need to put dy dx. So um, order matters unless we're doing it indefinitely. So for this case, Um, but the way you indefinitely integrate, it's the opposite of partial differentiation, which I made a video on. So since dy is first, what we treated it as is we treat it as it becomes we take this part out and we solve this integral, okay, and also without the dx. So now we're basically solving for this. We're solving for the integral of 4x plus 3y dy. And what does that equal? Well, since it's the opposite of partial differentiation, we're basically trying to take the integral of each one. So 4x is treated as a constant because it doesn't have a y, because we're integrating along the y. And so anything that doesn't have a y in it is a constant. And so this becomes no integral because we're solving it. It becomes 4xy plus 3y squared over 2. Okay, that's the answer to this integral. Then we're going to come back over here, and now we're going to have our integral of that, which I'm going to write it in here, but it's going to be dx. So it's almost like foiling, kind of doing this. And you could just imagine for a triple integral, it's the exact same thing, except you have a z. You have a dy dx dz, or dx dy dz, dz dy dx, any of that. So now I'm doing the integral of 4xy plus 3y squared over 2 dx. So now that, and I should draw this plus sign a little better. So now we have our 4xy. Our 4xy dx, we can put the constant in the front. The constant will be 4y because that doesn't have an x in it. So it's just going to be 4y x squared over 2. Okay, so that's our first term. And then our second term has no x in it, since it's just 3y squared over 2. So what do? Since that's technically just a constant in the x's perspective per se, we just add an x. So it becomes 3y squared x over 2. And then you could simplify this, but yeah, this is the answer. So this would represent the area from or a function for the area enclosed by this region, and we can put parameters here, like if we want to do 0 to 5 and 0 to 4, this would represent the area of this region from 0 to 5 in the y and 0 to 4 in the x. So it's kind of cool thing. I mean, if you think about it, like if you wanted to find the area of a rectangular region, all you would have to do is you would have to plug in the a, a line for y and for x, and plug in the area you want it to be. So like how far it goes up in the y and how far it goes up in the x. And then once you take the double integral of that, you'd find the area of that. And this figure would just it would have an area, but wherever it intersects these points, or how much it intersects those points, would represent the area of that. So yeah, I'm gonna make a video on definite integration for this. It's a couple small steps, but I think it's definitely worthy of a video. So yeah, thanks for watching, and tell me if you want me to make anything else. Thanks.